Now we are going to see the Hooke's law. So what is meant by Hooke's law? So Hooke is a scientist. He told that, okay, stress is directly proportional to strain. Correct, sir? So now we are taking a body. Okay, if you take a body, okay, if you apply force, automatically it changes its length. If you apply more force, automatically the more change. Okay, so stress is directly proportional to strain. Okay, this is known as Hooke's law. Okay, that means stress and strain both are proportional to each other. So stress is directly proportional to strain. This proportionality of constant we call it as K. So stretch is equal to K into strain, and this K is known as modulus of elasticity. So about this modulus of elasticity we will know, we will see that later. There are three types of modulus of elasticity. So simple Hooke's law. What is meant by Hooke's law? Stress is directly proportional to the strain. Okay, so stress and strain, they are proportional to each other. So stress is equal to K into strain. This proportionality of constant K is known as modulus of elasticity. So mathematically we can represent, this is stress, we know. So stress is equal to E into epsilon. Here epsilon, this is strain. E is known as modulus of elasticity. Okay, E is known as modulus of elasticity. So E is equal to E is known as modulus of elasticity. E is equal to formula is stress by strain. Okay, so strain don't have any units, so automatically whatever may be the units having stress is same for Young's modulus also. Okay, modulus of elasticity is having same units to that of stress. Okay, now the stress is Newton per meter square, the same units for modulus of elasticity also. Okay, now we are going to see the stress strain curve. So I have taken a spring here. So this spring is fixed at the top side and I am applying some forces. Okay, initially there is no force, so there is no elongation. If I apply some force, it changing its length by x. If I apply some more weight, that means force in this direction, it is changing its, okay, it is stretching some more, so the change in length is 2x. Okay, like that. So now what happened, I have taken strain on the x-axis and stress on the y-axis. Now I am varying this force or load and corresponding change in the length I am noting. So one side I am recording stress and one other side I am recording what is the strain. Okay, the typical stress strain curve is like this. Okay, generally initially stress is 0, strain is 0. Whenever you are applying stress force, automatically there is some strain, there is change in length. After certain time what happens, for small change in stress there is a big change in strain. Okay, now we will see the various points in this. Okay, so the first point is, see, from 0 to A. So between 0 to A what happens, the stress strain is, it is the linear. Okay, stress and strain both are approximate, they are both are proportional to each other. If you increase stress, corresponding increase in strain we can notice. Okay, so up to point A, so 0 to A, the stress and strain both are proportional to each other. This is the linear curve. Now after point A, what happens, if you apply the stress, there is a corresponding change in strain. okay, but it is not linear, it is non-linear. Okay, so finally from 0 to B, if you change the stress, strain also changes. But up to point A, the relation is linear, but after point A, that means from A to B, the relation is non-linear. Okay, that we have to observe from 0 to B. Now, this point B is known as yield point and corresponding stress is known as yield stress. Okay, corresponding stress is known as yield stress. That means up to point B. Okay, up to point B, if you apply stress, there is a change in this body changes its it changes its what is this? The length increases. Correct? There is some increase in length. Okay, so up to this point B, what happens? If you remove the stress, it will come back to its original position. Okay, so B is yield point up to this point. Okay, if you increase the stress, there is strain also increases, the body changes its length. If you remove the stress, that means if you remove the force on the body, it will come back to its position. But after point B, it won't come back to its position. Okay, so if you cross the point B, that is yield point or yield stress, now the body gets permanently deformed. Okay, it won't come back to its original position. So that is the difference between, that is the point B understanding. That means below B, the material, okay, up to point B, it acts as elastic material. So what is meant by elastic material, sir? So if you apply the force, it changes its length. Okay, after removing that force, it will come back to its original position. But after B, what happens? It won't come back to its original position. That means now that material is behaving like plastic material, so permanent deformation. Okay, so this is the importance of point B. Okay, and now if you observe, okay, the point, okay, this D is known as stress. Okay, what is this D? This D is known as breaking stress. That means up to D, up to this point, up to this stress, okay, ultimate stress or ultimate point, up to this stress the material withheld. Okay, after this point, at any time the material may fracture. Okay, after this point the material may get fracture. Okay, so this is the simple stress and strain curve. From this curve, so there are some important points. So if the first point is, now we are taking strain on x-axis and corresponding stress on the y-axis. Okay, now if you apply the stress, automatically the strain gets increased from 0 to A. Okay, the stress and strain both are proportional to each other and the curve is linear. In this case, if you remove the force, it will come back to its original position. That means material behaving like elastic material. Now after point A, if you increase the stress, the strain is also increasing, but the relation is non-linear. Okay, so from point A to B, the relation is non-linear, and at point B, though this is the point B, is known as yield point or yield stress. The corresponding stress is known as yield stress. That means up to this point, if you apply the stress, the strain increases, and if you remove the stress, the body come back to its original position. Okay, but if you cross the point B, now the strain also increases. Now the body is behaving like plastic material. That means the the deformation caused is permanent after point B. So up to point B, the material behaving like elastic material, and after point B, the material behaving like plastic material. Now this is the point D. This is known as ultimate point. Okay, ultimate point. Now this at this point, okay, breakdown point also we can known it as breakdown point. Okay, here the material will break it after this stress. At any time the material may get breakdown. So this particular point is fracture. E is known as, so at this point the material will get fracture. Okay. And there are some type of other materials. For example, if you take rubber, okay, some other materials, they elongate more even if you apply small forces. As compared to their length, they are elongating 2 to 3 times. Okay, those materials are known as elastomers. Okay, and the curve is also non-linear. Okay, and the curve is also non-linear. So this is a typical graph of a what is that? Aorta. So aorta is nothing but a big nerve. It is a big valve. It is a blood valve. It is taking blood from our heart to remaining parts. Okay, it is a big valve. It is elastic in nature, and its graph is like this. Okay, it is generally non-linear, and those materials are known as elastomers. For example, rubber. Okay, if you stretch the rubber, what happens? It will increase its length by 2 to 3 times to its original length, and even after removing it, the force, it will come back to its original position. So such type of materials are known as elastomers. Okay. Now the stretch strain graph. So here one more time. So the conclusion from the stress and strain graph, we can conclude the elastic material, whether it is elastic material, ductile materials, brittle materials, or elastomers. Okay, elastomers. Now see, up to point B. Okay, up to point B, the material is elastic in nature. After point B, the material is plastic in nature. Okay, that means up to point B, it will come back to its original position. After point B, it won't come back to its original position. And the difference, see, the point D is breaking stress, the point E is fracture point. So at this point, the material is ready to get fracture. Okay, and this is actual fracture point. If the distance is somewhat higher, okay, if these 2 points are widely spaced, then the material is known as brittle material, ductile materials. If these 2 points are very near, then those materials are known as brittle materials. So glass is the example for brittle materials, whereas some brass is also example for ductile materials. Okay. Now this portion, so in this graph, if you observe the point from 0A to 0 to A, this is linear portion. So in this linear portion, the stress and strain are directly proportional to each other. So this is the region where our Hooke's law validates. Now what is Hooke's law states? The stress is directly proportional to strain. Correct? Stress is directly proportional to strain. Okay, so sigma is proportional to strain. Okay, that is valid only in this region, that is 0 to A. Okay, so Young's modulus is known as stress by strain. Now elastic modules. Okay, elastic modules. So we know that the stress is directly proportional to strain according to the Hooke's law. Okay, so stress is equal to K times the strain. So now this proportionality of K is known as elastic module. So this K is known as modulus of elasticity or elastic moduli. Okay, elastic moduli or modulus of elasticity. So modulus of elasticity. So there are three types of modulus of elasticity. The first one is Young's modulus of elasticity denoted by Y, and the second modulus is shear modulus denoted by G, and the third one is bulk modulus denoted by B. Okay, so simple. So the modulus, elastic modulus means nothing but the modulus is the simple formula is stress by strain. If it is tensile stress by tensile strain, it is Young's modulus. If it is shear stress by shear strain, it is shear modulus. If it is volumic stress by volumic strain, then it is known as bulk modulus. So Young's modulus is denoted by Y, shear modulus is denoted by G, and bulk modulus is with B. Okay. Now we are going to see the Young's modulus. Young's modulus. So stress is directly proportional to strain. Okay, sigma directly proportional to epsilon. Now this proportionality constant is E. Okay, now this E is known as Young's modulus. Okay, now C is known as Young's modulus. So this is valid only in this region. Okay, linear region. Okay, here there is a simple formula. Okay, and a simple formula and a simple this also there. Initially there is a spring of length 4 meters. After putting some force, it is elongating by 2.5 mm. Now what is the Y? So the formula for Y is force per unit area by stress by strain. So stress is nothing but F by A, and strain is nothing but change in length by original length. You know the force, that is 10 newtons. You know the area, okay, pi r square or pi by 4 d square. You know the change in length 2.5 mm, and you know the original length, it is 4 meters. If you substitute these values in this formula, you will get the answer. Okay, now large stress and small stress. So I am taking a body, two bodies. Okay, so this is one body, and here it is one more body. If you observe, I am applying a force, same force for the both bodies. For the two bodies, I am applying the same amount of force. Okay, the area of cross section of the body, this body is very less as compared to area of cross section of this body. So according to our formula, stress is equal to force by area. Okay, so force is fixed in both the cases, whereas area is varying in both cases. If the area is less, automatically stress is more. If area is more, automatically stress is less. So this body is having lesser area, hence the stress is more in this body. Similarly, this body is having more area, so stress is more in this, stress is less in this body. So what is the observation? We want to decrease the stress, means we have to increase the area. So this is very, very important aspect in building, in designing the bridges and structures. Okay, similarly strain. Okay, so strain is, what is the formula? Strain, deformation by original shape. Okay, now I am taking two bodies. Okay, one, this is the first body and this is the second body. Both are having the same length L0. Okay, this body is now the same force I am applying in both cases, that is F only. Because of this force, this is compressive force, hence it is decreasing its length. So here the change in length is very high, here the change in length is very less. Okay, now what happens? Actually the formula is delta L by L. So strain formula is delta L by L. Okay, in both cases L is fixed, so the deformation, if more the deformation, the strain is more. So in first body the deformation is more, hence the strain is very large. In second case the deformation is very less, hence the strain is very less. Okay. Now stress by strain. Okay, stress by strain. Now I am applying a stress. Okay, if for that stress, if strain is less, automatically if you take steel body, okay, I am taking two bodies, steel body. Okay, I am applying some stress. Okay, the strain for the steel body, the strain is the compression, the change in its length is very less. That means the strain is very less, so automatically the overall this one is large. Okay, it is nothing but modulus of elasticity. Stress by strain is modulus of elasticity. Okay, so for a particular amount of stress, if strain is less, then the value is large. That means if Y is large, that material is very strong. Similarly, if you take some other material, okay, you take rubber. Okay, for the same force, for the rubber, what happens? The strain is more. That means the strain more means the complete value decreases, small. So the Y is small, the modulus of elasticity is small, means it is the weak material. So from this we can conclude that a strong material is having more value of Y, elasticity, modulus of elasticity. If the modulus of elasticity is very less, then it is the weak material. Okay. Now in this table we are going to see the typical values of the Young's modulus. Okay. Now according to our previous observation, the strong material should have very high value of the Young's modulus. So from these materials, steel is the very toughest, strongest material. So its value is 200. So the Young's modulus is 200 for the steel. The next is iron. Okay, and if you see the wood. Okay, for the wood, the value is very less. That means from this table, if the Y is less, the material is not stronger. If Y value is increases, the material is stronger. Okay. So if you like our video, please subscribe the video and like it, and please press the bell icon. Okay. You can also follow us on WhatsApp 80730 41192.